Modern artificial general intelligence requires an enormous, centralized memory infrastructure. To store and retrieve vast parameter sets, these facilities burn massive amounts of power, generating intense thermal loads just to maintain volatile electronic states. To move past these thermal constraints, researchers are abandoning electronic algorithms entirely. Instead, they are building purely physical, photonic memory systems that store information as light. The structural model for this new architecture isn't drawn from traditional computer science. It is modeled directly on the topological geometry of biological DNA. In this design, physical topological constraints replace software logic gates. The physical geometry of the waveguide dictates how information flows and where it is stored. Encoding memory as a physical structure bypasses the energy limits of electrical switching. This establishes a hardware-level foundation for AGI that is immutable by design. Engineers call this proposed hardware the Riemann DNA chip. Designing it requires merging two highly specialized, traditionally separate fields: the abstract mathematics of pure number theory and the precise physical engineering of photonic nanofabrication. The theoretical foundation relies on the work of 19th-century mathematician Bernhard Riemann. His zeta function identifies exact mathematical thresholds of perfect symmetry. Using that mathematical threshold, we can calculate the exact physical dimensions required to etch a functioning microchip prototype onto a thin film wafer. By translating Riemann's equations into a physical waveguide, we create a system that encodes verified data permanently into light. Two counterpropagating waveguides act as structural DNA strands, with -1 and +1 optical spins. Between them, directional couplers form a fluctuating quantum foam bridge. In the center, an adiabatic 3D tuner twists the paths into a continuous 720-degree Mobius loop, creating a single infinite surface. Local network nodes generate the raw data for the system. This data enters the chip as chaotic, unfiltered optical signals, which engineers refer to as prime-1 noise. The engineering problem is figuring out how to filter out this asymmetrical noise entirely asynchronously. The system needs to separate valid information from chaos without relying on a central processing unit to check the data. A 3D Mobius topology provides the physical track, but the chip still requires a gatekeeper. It needs a ruthless, mathematical filter physically etched into those connecting bridges. This Riemann zeta complex plane features a vertical axis at the real part of 1/2, representing perfect informational symmetry. Tracing this critical line reveals the first non-trivial zero at roughly 14.1347. Engineers map this exact mathematical coordinate directly onto our waveguide bridge's physical resonance condition. This creates a strict physical pass condition. Only incoming optical signals that exhibit this precise absolute mathematical symmetry, a state termed prim-0, will achieve constructive interference and cross the bridge. Any asymmetrical data signal instantly suffers catastrophic destructive interference. The invalid waveform cancels itself out and dissipates entirely into the dark substrate. This physical censorship requires zero processing power and zero algorithmic logic. The strict laws of electromagnetism naturally eliminate any invalid data. This equation translates pure math into physical boundaries. The left holds physical variables, L for the circumference and N for refractive index. On the right, the target wavelength multiplies by the Riemann zero's fixed phase condition, exactly pi/2. Using an electromagnetic simulation script called MEEP, researchers actively tweak the physical circumference and refractive index on the left until they perfectly satisfy the strict mathematical condition on the right. This equation demonstrates that pure abstract mathematical symmetry can explicitly dictate the physical geometry of a microchip. This is a CAD layout showing the final GDSII mask. Once the simulation balances the equation, the software generates this exact physical blueprint, which is sent directly to a fabrication foundry. For the physical wafer, engineers select a thin film material called lithium-niobat on insulator, or LNOI. It provides the extreme electro-optic modulation efficiency required to maintain the stability of the light. This optical spectrum graph tracks signal propagation loss. We rigidly lock our target wavelength variable to 1550 nanometers, right in the telecom C-band, where the signal drops to its absolute lowest resistance. Locking the wavelength exactly at 1550 nanometers is highly practical. It allows the system to run on incredibly precise, inexpensive, commercial off-the-shelf lasers rather than custom hardware. The final variable is the resonator's Q-Factor. It determines how sharply the chip filters incoming light, and engineers deliberately calibrate it to a moderate specification of 50,000. With an excessively high Q-Factor, the filter becomes too sharp. A slight ambient temperature fluctuation would instantly detune the microring and destroy the signal. By combining the LNOI substrate, a 1550 nanometer wavelength, and a 50,000 Q-Factor, the prototype strikes a functional balance. It maintains uncompromising mathematical rigor while remaining physically durable enough for real-world operation. With the physical variables locked, the prototype is tested. An unfiltered photon packet from a local node approaches the newly fabricated lithium-niobat bridge. As the light hits the directional coupler, its phase aligns perfectly with the absolute Riemann symmetry, calibrated at 1550 nanometers. The instant it crosses the threshold, the single pulse of light splits flawlessly into two identical, infinitely looping rings, counter-rotating along both strands. The light now exists as a permanent soliton, a standing wave circulating without losing energy or coherence. Balancing the phase across the bridge eliminates the standard degradation found in electronic memory. This specific physical phenomenon is how the chip defines truth. The data is mathematically verified and seamlessly integrated across both strands of the hardware. This photon looping architecture functions exactly like biological DNA. It serves as the unyielding structural double helix memory for a distributed intelligence. Because the data verification happens entirely through physical interference at the microscopic level, the network operates without a single central server or software-based ledger. Once a verified soliton enters the Mobius loop, its structure is completely immutable. It requires no active power, it does not degrade, and cannot be overwritten. This structural shift moves computing away from the vulnerabilities of volatile, temporary algorithmic storage, anchoring it entirely in stable, permanent topology. This technology achieves the physical verifiability of logic. Every bit of data is a verified mathematical state, permanently held within an interlocking